Hello there, and welcome to Science for Sleep, a quiet place where the universe's deepest puzzles become gentle companions for the evening. I'm glad you're here tonight because we're about to settle into something remarkable. It's been among 30 years since Einstein first began reshaping how we see reality, 130 years since space-time entered human thought as more than just space and time sitting separately. And yet even now, after more than a century of brilliant minds working through the mathematics, building extraordinary instruments, and testing predictions with astonishing precision, space-time remains fundamentally mysterious. Not in a disappointing way, but in a way that feels almost like the universe is quietly holding something back, offering clues but never quite the whole picture. Before we drift any further, I'd love to know something small and grounding. Where are you listening from tonight? What does the room around you feel like right now? And if these gentle explorations help you unwind, or if they offer a calm companion for settling into sleep, it would mean a lot if you'd like the video or subscribe. It helps this quiet corner reach others who might need something soft and steady to drift off to, but only if it feels right. For now, let's wander through that mystery together, not rushing toward answers, but letting the strangeness of it settle around us like a soft question that doesn't demand to be solved immediately. Have you ever wondered why your phone knows exactly where you are, even though something invisible and impossible to touch is bending all around you right now? There's a fabric woven through everything, determining where here actually is and when now happens, yet you've never seen it, never felt its texture, never heard it rustle as you move through your day. This fabric is space-time, and it's working quietly in the background of every single moment you experience, shaping reality in ways so subtle that your senses simply weren't built to detect them. When you stand still in your room right now, you might think you're not moving, but the truth is far stranger. You're racing through space-time at the speed of light, except nearly all of that motion is aimed in one direction, through time itself, carrying you forward second by second into what we call the future. Only a tiny fraction of your motion goes through the 3 dimensions of space, which is why walking across a room feels so slow compared to the relentless passage of time. This might sound abstract, almost philosophical, but it's as real and measurable as the ground beneath your feet. Every choice about where to go and when to arrive is a choice about how to move through this combined landscape of space and time. When you decide to meet someone at a coffee shop tomorrow at 3 in the afternoon, you're not just picking a location in space and a moment in time separately. You're selecting a specific point in space-time, a precise intersection of where and when that exists as a unified thing. The coffee shop at 3 tomorrow is a different place in space-time than the Thale coffee shop at 9 this morning, even though the building hasn't moved an inch through space. Space-time treats these as fundamentally different locations because the fabric itself includes time as one of its dimensions. Now let's turn to something that feels even more familiar: gravity. You've felt it your entire life as a downward pull, a force yanking objects toward the Earth's center. Drop your phone and it falls. Jump and you come back down. Stand on a scale and it measures the force of gravity pulling you against it. Every part of that description sounds completely natural, completely obvious, except it's wrong. Not wrong in the sense that the observations are false, but wrong in the deeper sense of what's actually happening. Gravity is not a force pulling you downward. Gravity is the shape of space-time curving around massive objects, and you're simply following the straightest possible path through that curved geometry. Imagine rolling a marble across a flat table. It travels in a straight line because the surface is flat. Now imagine placing a heavy bowling ball on a stretched rubber sheet. The sheet dips around the ball, creating a curved surface. Roll the marble near the bowling ball and it curves inward, not because the bowling ball is reaching out and grabbing it, but because the surface itself is no longer flat. The marble is still trying to go straight, but straight on a curved surface looks curved from the outside. This is what's happening with gravity, except the curved surface is space-time itself, and massive objects like Earth create curves in that 4-dimensional fabric. You're not being pulled toward Earth. You're trying to move straight through space-time, but Earth's mass has curved space-time around it, and moving straight through curved space-time means following a path that brings you toward the planet's surface. When you stand on the ground, you're actually being prevented from following your natural path through space-time. The floor pushes up against you, and you feel that push as weight. This leads to one of the most beautiful and strange facts about falling. When you jump off a diving board or ride a roller coaster down a steep drop, you feel weightless. Your stomach lifts, your body feels light, and for those few seconds, gravity seems to have vanished. But gravity hasn't gone anywhere. What's actually happened is that you've stopped resisting it. You're finally following the natural curve of spacetime without anything pushing against you. Astronauts in orbit feel weightless for the same reason. They're not beyond Earth's gravity. They're falling toward Earth constantly, but they're also moving forward fast enough that they keep missing it, falling around the planet in an endless curve. That continuous fall is their natural path through curved spacetime, and because nothing resists that path, they feel, no, wait at all. This isn't just theory or abstract mathematics. We can measure spacetime's curvature with extraordinary precision, and we do it every single day with technology you probably have in your pocket right now. GPS satellites orbit Earth at altitudes around 20,000 kilometers, and they carry atomic clocks that tick with incredible accuracy. These satellites send signals to your phone, and by comparing the timing of signals from multiple satellites, your phone calculates your position. But here's where it gets interesting. Those clocks in orbit don't tick at the same rate as clocks on Earth's surface. Time itself runs faster up there because spacetime is less curved at higher altitudes. Earth's mass curves spacetime most intensely near its surface, and that curvature affects how quickly time passes. The difference is tiny, only about 38 microseconds per day faster in orbit compared to the ground. But GPS systems are so precise that ignoring this difference would cause your location to drift by several kilometers within a single day. Engineers building GPS had to program the satellites to account for this time difference, adjusting their clocks to compensate for the fact that they experience time differently than you do down here. Every time your phone tells you to turn left in 200 meters, it's using calculations that account for curved spacetime. Every navigation app, every mapping service, every delivery truck route depends on understanding that time flows at different rates depending on where you are in Earth's gravitational field. This is everyday proof that spacetime bends, that Einstein's strange geometric picture of gravity is not just correct, but necessary for modern technology to function. The implications ripple outward from there. If time runs faster at higher altitudes, then your head ages slightly faster than your feet. The difference is absurdly small, only about 90 billionths of a second over an entire lifetime, but it's real. Clocks placed on tables tick faster than clocks placed on floors. Mountains age faster than valleys. Satellites age faster than sea level. Time is not a universal river flowing at the same rate everywhere. It's a dimension woven into spacetime's fabric, and that fabric curves and stretches depending on the mass nearby. This brings us to something even more peculiar. You're always moving through spacetime at the speed of light, not through space at light speed, which would require infinite energy and is impossible for anything with mass, but through the combined fabric of space and time together. Think of it like a budget of motion. You have a fixed total speed through spacetime, always exactly the speed of light, and you can divide that motion between moving through space and moving through time. When you sit still, nearly all your motion is through time. Seconds tick by at their normal rate because you're using almost your entire budget of spacetime motion to travel through the time dimension. When you start moving through space, walking or driving or flying, you redirect a tiny bit of that motion away from time and into space. This means time passes slightly slower for you when you're moving. Again, the effect is tiny at everyday speeds, but it's measurable with precise clocks. Astronauts returning from months in orbit are a fraction of a second younger than they would have been if they'd stayed on Earth, not because orbit stopped their aging, but because moving fast through space means moving slightly slower through time. The faster you move through space, the slower you move through time, and this trade-off is built into space-time's geometry. Light itself moves through space at maximum speed, which means it doesn't move through time at all. From a photon's perspective, if such a thing could exist, no time passes during its journey. A photon emitted from a distant star billions of light years away experiences no duration between leaving that star and entering your eye. Its entire journey is instantaneous from its own frame of reference because all of its spacetime motion is devoted to moving through space, leaving none for moving through time. This is the fabric you live inside without noticing. A four-dimensional landscape where space and time interweave, where massive objects curve the geometry, where your motion through one dimension affects your motion through others, where satellites age faster than surface dwellers, and falling feels like weightlessness, because you're finally moving along spacetime's natural contours. Every step you take, every breath you draw, every moment you experience is shaped by this invisible structure. You can't see it bend or feel it flex, but it's there, determining where here is and when now happens, quietly holding the reality together in ways that still surprise us even after more than a century of knowing it exists. What if the moment you're experiencing right now isn't the same now that someone else is experiencing, even if you're standing right next to each other? This sounds impossible because we grow up believing that time is universal, that everyone everywhere shares the same present moment ticking forward together in perfect synchronization. But space-time reveals something far stranger lurking beneath this comfortable assumption. Two people moving at different speeds don't just measure time differently. They actually disagree about what events are happening simultaneously. If you're sitting still reading these words while someone else rushes past you at high velocity, the events they consider to be occurring right now in distant parts of the universe are genuinely different from the events you consider to be happening at this exact instant. This phenomenon goes by the technical name relativity of simultaneity, but the implications are so profound that they reshape what it means for anything to be present or current. Imagine two friends standing on opposite ends of a moving train. Lightning strikes both ends of the train car at precisely the same moment according to someone watching from the platform. The person on the platform sees both flashes simultaneously because the light from each strike travels the same distance to reach their eyes. But what about someone standing in the middle of the moving train? They're moving toward one lightning strike and away from the other. The light from the front strike reaches them first, followed moments later by light from the rear strike. From their perspective, the strikes didn't happen simultaneously. They occurred at different times. Neither observer is wrong. There's no absolute truth about whether those events happened at the same moment. Simultaneity depends entirely on your motion through space-time. This gets even more peculiar when you scale it up. Right now, as you sit wherever you are, there exist events on a distant planet that you would call simultaneous with this moment. But if you stood up and started walking, the set of distant events that count as simultaneous would shift. Walking forward through space tilts your slice through space-time, changing which faraway events belong to your now. Moving towards something brings its future into your present. Moving away from something pushes its present into your past. The faster you move, the more dramatic this tilt becomes. At everyday speeds, the effect is immeasurably tiny, but it's real. Your now is not a universal flat plane cutting through space-time. It's a tilted slice that depends on how you're moving. Even more startling is what happens right here in your own body due to gravity's influence on time. Your head exists in a slightly weaker gravitational field than your feet because it's farther from Earth's center. This means time flows faster for your head than for your feet. Over the course of an entire lifetime, your head ages about 90 billionths of a second more than your feet. This isn't a metaphor or approximation. The cells in your brain literally experience more elapsed time than the cells in your toes. If you could place an atomic clock next to your head and another next to your feet, the one by your head would tick faster. Every moment of your existence unfolds across slightly different rates of time depending on altitude. Stand on a ladder and your head ages even faster relative to your feet. Lie down flat and the effect disappears because both ends of your body occupy nearly the same gravitational potential. This reveals something fundamental about space-time's nature. You cannot separate space from time as if they were independent ingredients mixed together. They trade off against each other, like currency and an exchange. Moving through more space means moving through less time. Experiencing stronger gravity means time passes more slowly. Climbing higher in a gravitational field means time flows faster. Every change in your position through space affects your motion through time. Every change in your velocity redistributes how much of your fixed space-time speed goes towards spatial motion versus temporal motion. The traditional view imagines space as a three-dimensional stage where events unfold as time marches forward separately. But space-time fuses these into a single four-dimensional structure where what you call space and what you call time depend on your perspective and motion. An event that seems to happen purely in time from one viewpoint, occurring at the same location but at a different moment, might appear to someone moving differently as an event that happens both at a different time and a different place. Space and time mix and blend depending on the observer. This leads to what might be the most unsettling implication of space-time physics. If simultaneity is relative, If different observers slice through space-time differently, then in what sense does the present moment exist as something special? Einstein's equations treat time as just another dimension, mathematically similar to the three spatial dimensions. The past isn't gone and the future isn't yet to come. They're just different regions of space-time, as real and existing as the place where you are now. This perspective is often called the block universe. Imagine all of space-time laid out as a single unchanging four-dimensional structure. Your entire life, from birth to death, exists as a continuous thread through this block. What you experience as the present moment is just your consciousness moving along that thread, but the thread itself already exists in its entirety. Yesterday is still there, a region of space-time you've moved past. Tomorrow already exists as a region you haven't reached yet. Nothing is flowing or changing in the block universe. Everything simply is, spread out across four dimensions. This contradicts our deepest intuitions about time. You feel the present moment as uniquely real, as the knife edge between a fixed past and an open future. You sense time flowing, carrying you forward from what was into what will be. You remember yesterday but not tomorrow, suggesting they have fundamentally different statuses. Yet space-time physics offers no support for this feeling. The equations work equally well running forward or backward. They contain no special marker for now, no indication that one moment is privileged over others. Past, present, and future appear to exist on equal footing within spacetime's geometry. Some physicists and philosophers embrace the block universe as the true nature of reality, arguing that our sense of flowing time is an illusion created by consciousness. Others resist this conclusion, seeking ways to restore a genuine distinction between past, present, and future even within spacetime's framework. The tension remains unresolved. What makes this especially peculiar is that the block universe seems to eliminate free will and genuine change. If your future already exists as solidly as your past, laid out in the spacetime block, then in what sense are your choices real? How can anything be genuinely undecided if the outcome already exists in a future region of spacetime? These questions touch on deep mysteries about consciousness, causation, and the nature of possibility. Spacetime physics describes the geometry beautifully, but leaves the experiential questions hanging. You can measure time dilation, test simultaneity's relativity, confirm that clocks at different heights tick at different rates. Every prediction checks out with extraordinary precision, yet the theory seems to strip away the flowing, dynamic quality of time that feels so fundamental to lived experience. Your head ages faster than your feet by a measurable amount, yet both ends of your body feel like they're existing in the same present moment. Events that are simultaneous for you happen at different times for someone moving past you, yet you both feel like you're experiencing the real now. The past feels gone and the future feels open, yet space-time suggests they're equally real regions of a fixed, four-dimensional structure. These contradictions don't indicate errors in the physics. They reveal gaps in our understanding, places where the mathematical description and human experience point in different directions. Space-time works magnificently as a tool for prediction and calculation. It's been tested thousands of times and passed every examination, but it leaves the strangeness of time's flow unexplained, perhaps even denied. This is part of why space-time remains mysterious even after more than a century. We understand its geometry but not its meaning. We can calculate how it curves but not why one direction through it feels so different from the others. The fabric reveals its mathematical structure readily enough, but the experiential texture of moving through it, the feeling of now advancing and the past receding, remains as puzzling as ever. How did one patent clerk working alone in Switzerland manage to overturn centuries of perfectly sensible physics that had explained everything from falling apples to planetary orbits? For more than 200 years, Isaac Newton's framework had provided humanity with a magnificently successful description of motion and gravity, built on foundations that seemed utterly solid and intuitive. Newton envisioned absolute space as a vast, unchanging stage, where events unfolded, a three-dimensional container that existed independently of anything it held. Time, in his view, flowed uniformly everywhere, ticking away at the same rate whether you measured it on Earth or Jupiter or in the depths of interstellar emptiness. This absolute time meant that simultaneity was universal. If two events happened at the same instant, they happened at the same instant for everyone, regardless of where they were or how they moved. Clocks might run fast or slow due to mechanical imperfections, but true time, The time of the universe itself marched forward identically everywhere. Gravity in. Newton's picture was a force, an invisible pull that massive objects exerted on each other across empty space, weakening with distance but never quite vanishing. This framework felt natural because it matched everyday experience so perfectly. Things fall down, planets orbit in ellipses, pendulums swing with predictable periods. All of it made sense within Newton's absolutes. Then came light, and everything crumbled. Throughout the 1800s, physicists developed increasingly sophisticated understanding of electricity and magnetism, culminating in James Clerk Maxwell's equations that unified these phenomena and revealed something unexpected. Light emerged from Maxwell's mathematics as an electromagnetic wave, and the equations predicted its speed with remarkable precision. But here's what shattered the Newtonian worldview. Maxwell's equations gave light a specific velocity without a reference to any observer's motion. Unlike sound, which travels at different speeds depending on whether you're moving toward or away from its source, light seemed to have one fixed speed built into the fabric of electromagnetism itself. This created an enormous puzzle. Speed is always measured relative to something. A car travels 60 kilometers per hour relative to the road. Sound moves at 340 meters per second relative to the air carrying it. If light has a definite speed, what is it moving relative to? Physicists proposed that space must be filled with an invisible medium called the luminiferous ether, a substance that permeated everything and carried electromagnetic waves the way air carries sound. Light would travel at its characteristic speed relative to this ether, and Earth moving through the ether should create detectable effects. In 1887, Albert Michelson and Edward Morley designed an exquisitely sensitive experiment to measure Earth's motion through the supposed ether. They reasoned that as Earth orbited the Sun, it must be moving through the ether in different directions at different times of year. Light travelling in the direction of Earth's motion should be slowed by the ether wind, while light travelling perpendicular should be unaffected. Their interferometer could detect differences far smaller than expected. The results stunned everyone. No matter which direction they looked, no matter what time of year they conducted the measurement, light travelled at exactly the same speed. There was no ether wind. Earth's motion through space had zero effect on light's velocity. Subsequent experiments confirmed this bizarre finding again and again. Light's speed remained constant regardless of the observer's motion, defying every intuition about how speed should add and subtract. This is where Einstein entered, not with new experimental data, but with a willingness to take the evidence seriously and follow it wherever it led. In 1905, he published Special Relativity, proposing something radical. What if light's constant speed isn't a puzzle to be solved but a fundamental feature of nature? What if instead of light adjusting to fit our assumptions about space and time adjust to keep light's speed constant? This meant abandoning Newton's absolutes. Space cannot be a fixed stage and time cannot flow uniformly if light speed must remain constant for all observers. Instead, Einstein proposed that space contracts and time dilates in just the right amounts to preserve light's velocity. If you chase after a light beam at tremendous speed, you don't catch up to it because from your perspective, distances shrink ahead of you and time slows down, conspiring to keep the light beam receding at the same rate as always. 10 years later, Einstein extended these ideas into general relativity, tackling gravity itself. Newton had left gravity mysterious. Massive objects somehow reached across empty space to pull on each other. But what actually transmitted this force? Einstein proposed that gravity isn't a force at all. Mass curves spacetime and objects moving through curved spacetime follow paths that look like gravitational attraction from the outside, but are actually just the straightest possible routes through warped geometry. Imagine placing a heavy ball on a taut rubber sheet. The sheet sags around the ball, creating a depression. Roll a marble near the depression and it curves inward, not because the ball pulls it, but because the surface is no longer flat. The marble follows the contours of curved space. This metaphor helps visualize how mass warps geometry, though it's incomplete because the rubber sheet exists in a larger three-dimensional space and sags downward under real gravity. Actual space-time doesn't curve into anything external. It curves intrinsically, bending back on itself through its own dimensions. The curvature is in the relationships between points, not in how those points sit within some higher dimensional space. This geometric view transformed what gravity means. Newton described gravity as a force transmitted instantly across space. Einstein revealed it as the local shape of spacetime. A planet doesn't orbit because the sun pulls it. The planet moves straight through spacetime that happens to be curved by the sun's presence. What looks like an elliptical orbit through space is actually a helical path through spacetime, spiraling through the time dimension while tracing an ellipse through spatial dimensions. The shift from force to geometry changed physics at its foundations. Suddenly gravity wasn't something added to spacetime. Gravity was spacetime's structure, inseparable from the fabric itself. Mass tells spacetime how to curve. Curved spacetime tells mass how to move. The two concepts interlock completely. Einstein's revolution felt gentle because it didn't discard Newtonian physics so much as reveal it as an approximation. For slow speeds and weak gravity, spacetime curves so slightly that Newton's absolutes work beautifully. The differences only become noticeable near light speed, or in intense gravitational fields. GPS satellites, particle accelerators, and black hole observations all confirm Einstein's geometric picture with extraordinary precision. Yet this success creates deeper mysteries. If spacetime is geometry, what is it made of? If mass curves it, does spacetime have substance? Can geometry itself be fundamental, or must it emerge from something more basic? Einstein answered what gravity does without fully explaining what gravity is. The mathematics works magnificently. Predictions match observations to remarkable accuracy. But the conceptual foundation, the question of spacetime's ultimate nature, remains as mysterious now as it was when Einstein first glimpsed that space and time must flex to preserve light's constancy. Can you imagine publishing a theory so radical that it predicts phenomena nobody has ever observed? Then waiting years while the universe slowly reveals whether you are brilliant or delusional? Einstein's general relativity made predictions so precise and so strange that they seemed almost designed to be proven wrong. Yet every single one has been confirmed with accuracy that borders on the eerie. The first victory came from solving a mystery that had troubled astronomers for decades. Mercury, the innermost planet, follows an elliptical orbit around the Sun, but that ellipse itself rotates slowly over time, a phenomenon called precession. Newton's gravity predicted most of this precession based on the gravitational tugs from other planets, but observations showed Mercury precessing slightly faster than calculations allowed. The discrepancy was tiny, only 43 arc-seconds per century, roughly the width of a human hair viewed from a kilometre away. Astronomers proposed various explanations, including an undiscovered planet closer to the Sun, but none satisfied the data. When Einstein completed his field equations in November 1915, he immediately applied them to Mercury's orbit. The equations describing curved spacetime around the Sun automatically produced the extra precession without requiring any new assumptions or hidden planets. The curvature near the Sun, slightly more intense than Newton's theory predicted, caused Mercury to trace a path that rotated at exactly the observed rate. Einstein later described this moment as giving him heart palpitations, a physical reaction to realizing his geometric theory of gravity explained something Newton's force-based version could not. This wasn't just confirming a prediction, it was solving a genuine astronomical puzzle that had resisted explanation for half a century. 4 years later came an even more dramatic test. Einstein's equations predicted that light passing near a massive object should bend, following the curved spacetime around it. Newton's theory also predicted some light bending because photons carry energy, and energy has gravitational effects. But Einstein's prediction was twice as large. The difference was measurable but required observing starlight grazing the sun's edge, normally impossible because the sun's brightness drowns out nearby stars. A total solar eclipse provided the only opportunity. In May 1919, Arthur Eddington led expeditions to observe an eclipse from 2 locations, Sobral in Brazil and Príncipe Island off Africa's west coast. During totality, they photographed stars near the sun's darkened disk. Months later, after careful analysis comparing the stars' apparent positions during the eclipse with their positions when the sun was elsewhere in the sky, the results confirmed Einstein's prediction. Starlight had bent by roughly 1.75 arc-seconds, matching general relativity's calculations and doubling what Newton would have predicted. Headlines around the world proclaimed that space was curved, and Einstein became an international celebrity overnight. The confirmation transformed relativity from abstract mathematics into tested physics. Decades passed before technology advanced enough to test another key prediction. In 1971, Joseph Haffel and Richard Keating placed atomic clocks aboard commercial aircraft and flew them eastward around the world, then westward, comparing the travelling clocks against reference clocks on the ground. Special relativity predicted that clocks moving through space should tick slower, while general relativity predicted that clocks at altitude, in weaker gravity, should tick faster. The two effects partially cancel for eastward flight and reinforce for westward flight. When the experiment concluded, the clocks had gained and lost nanoseconds, exactly as Einstein's combined theories predicted. Eastward travel produced a net time loss. Westward travel produced a net time gain. The universe was keeping perfect score, accounting for both velocity and altitude effects, with precision measurable only by atomic clocks. 3 years later, astronomers discovered something even more remarkable. Russell Hulse and Joseph Taylor found a binary pulsar system, two neutron stars orbiting each other at tremendous speed while emitting regular radio pulses. General relativity predicted these stars should emit gravitational waves, ripples in space-time itself, carrying energy away from the system. As the stars lost energy, their orbit should gradually shrink, causing the orbital period to decrease at a calculable rate. Over years of careful observation, Hulse and Taylor tracked the orbital decay with extraordinary precision. The stars were spiraling inward at exactly the rate Einstein's equations predicted, losing energy to gravitational waves despite those waves being far too weak to detect directly at Earth. This binary pulsar became an indirect but incredibly precise test of general relativity's most exotic prediction, confirming that space-time itself can wave and ripple, carrying energy across cosmic distances. Perhaps the core, most practical confirmation comes from technology millions of people use daily. Global Positioning System satellites orbit Earth, broadcasting precise timing signals. Your phone receives signals from multiple satellites and calculates position by comparing arrival times. But this only works if the system accounts for relativistic effects. Satellites travel at about 14,000 kilometers per hour, causing special relativity's time dilation to slow their clocks by about 7 microseconds daily. Simultaneously, they orbit at altitudes around 20,000 kilometers where gravity is weaker, causing general relativity's gravitational time dilation to speed their clocks by about 45 microseconds daily. The net effect is roughly 38 microseconds per day faster in orbit. Without corrections, GPS positions would drift by kilometers within hours. Engineers programming these satellites must include both special and general relativistic adjustments. Every successful navigation, every accurate arrival time, every precisely located delivery demonstrates that space-time curvature is real and measurable. Modern smartphones carry technology that wouldn't function if Einstein had been wrong. Physicists have since conducted thousands of additional tests. They've measured frame dragging, the twisting of space-time around rotating masses. They've confirmed time dilation using particles in accelerators. They've tested the equivalence principle, that gravitational and inertial mass are identical to extraordinary precision. They've observed stars orbiting the supermassive black hole at our galaxy's center, their trajectories matching general relativity's predictions. They've detected gravitational waves directly using laser interferometers, confirming not just their existence but their precise waveforms. Every test strengthens confidence that space-time curvature genuinely describes gravitational phenomena. What makes these confirmations so compelling is their variety. General relativity doesn't just explain one anomaly. It correctly predicts planetary orbits, light deflection, time dilation at different speeds and altitudes, orbital decay in binary systems, gravitational redshift, frame dragging, black hole properties, cosmological expansion, and gravitational wave signals. The theory's mathematical structure locks these predictions together. You cannot adjust one without affecting others. The fact that such diverse phenomena all conform to a single geometric framework suggests something profound about reality's structure. These aren't coincidences or approximations, they are precise confirmations of space-time's curvature. Yet for all this success, for all the validated predictions and technological applications, fundamental mysteries remain. We know space-time curves, but not what it curves within or what it's made from. We can calculate its geometry, but cannot reconcile that geometry with quantum mechanics. We've confirmed Einstein Einstein's description of what gravity does without understanding what gravity ultimately is. The astonishing accuracy of these predictions makes the remaining mysteries more puzzling, not less, because they show that space-time is undeniably real, while simultaneously revealing that we don't fully grasp its nature. What does space-time sound like when two black holes collide, and how did scientists manage to hear something that happened over 1 billion light-years away? On September 14, 2015, exactly 1 century after Einstein published his field equations, twin detectors in Louisiana and Washington state registered a signal lasting less than 1/5 of a second. This signal, a faint vibration in space-time itself, had travelled across more than 1 billion light-years, carrying information about an event so violent it briefly outshone all the stars in the observable universe combined. Two black holes, each roughly 30 times the Sun's mass, had spiralled into each other at half the speed of light before merging into a single larger hole. The collision converted 3 solar masses worth of matter into pure gravitational wave energy, sending ripples through space-time that eventually reached Earth as a distortion smaller than 1,000th the diameter of a proton. LIGO, the Laser Interferometer Gravitational Wave Observatory, consists of L-shaped facilities with arms stretching 4 kilometers in perpendicular directions. Laser light bounces between mirrors at each arm's end, and when a gravitational wave passes through, it briefly stretches space in one direction while compressing it in the perpendicular direction. The lasers detect these minuscule changes in arm length by watching for shifts in how the reflected beams interfere with each other. The challenge is extraordinary because countless sources of vibration, from passing trucks to distant earthquakes to quantum fluctuations, constantly shake the mirrors. Isolating a genuine space-time ripple from this sea of noise requires suspending the mirrors on elaborate isolation systems and using 2 widely separated detectors to confirm that the same signal appears in both locations with the appropriate time delay. When the September signal arrived, it matched theoretical predictions so precisely that scientists could reconstruct the entire merger. The waveform began as a slow oscillation, the chirp of 2 black holes orbiting each other. As they drew closer, the frequency increased, rising in pitch like a sound wave climbing the musical scale. The final moments produced a rapid crescendo before abruptly cutting off as the holes merged into one. Then came the ringdown, a brief period where the newly formed black hole vibrated like a struck bell before settling into a stable configuration. Converting these space-time oscillations into sound frequencies produces an audible chirp, a rising tone that sweeps upward in a fraction of a second. This is what space-time sounds like when massive objects collide, a cosmic whisper that travels for eons before reaching detectors sensitive enough to register its passing. Since that first detection, LIGO and its international partners have identified dozens more gravitational wave events. Some involve black hole mergers of various masses. Others capture neutron-star collisions that simultaneously produce electromagnetic signals, allowing astronomers to observe the same event through both light and space-time ripples. Each detection confirms general relativity's predictions, while providing new information about dense matter, black hole populations, and the universe's expansion rate. Gravitational wave astronomy has transformed from theoretical possibility into observational reality within just a few years. 4 years after LIGO's breakthrough, another technological marvel achieved something equally stunning. The Event Horizon Telescope combined 8 radio observatories scattered across 4 continents into a virtual telescope the size of Earth itself. For several nights in April 2017, this planetary array focused on the supermassive black hole at the centre of galaxy Messier 87, located 55 million light-years away. The resulting image, released in April 2019, showed a dark circular shadow surrounded by a glowing ring of superheated matter. This shadow marks the black hole's event horizon, the boundary beyond which space-time curves so severely that nothing escapes. The size, shape, and asymmetry of the shadow match general relativity's predictions with remarkable fidelity. One side appears brighter because matter orbiting near light speed emits more radiation when moving toward us. The shadow's diameter corresponds to a black hole of roughly 6.5 billion solar masses, agreeing with estimates from stellar motions near the galaxy's core. Imaging this shadow required synchronizing observations using atomic clocks, combining data with supercomputers, and pushing radio astronomy techniques to their absolute limits. The result provided visual confirmation that black holes exist as general relativity describes them, with event horizons and photon spheres exactly where the mathematics predicts. Even more subtle tests have confirmed relativistic predictions. Gravity Probe B, a satellite experiment launched in 2004, carried 4 gyroscopes into polar orbit to measure frame dragging, the slight twisting of spacetime caused by Earth's rotation. According to general relativity, a spinning mass drags spacetime around with it, causing gyroscopes to slowly drift from their initial orientations. Over a year of observations, accounting for numerous confounding effects, the spacecraft measured this drift with precision better than 1%. Earth's rotation pulls spacetime around by tiny amounts, creating a vortex that affects anything orbiting through it. This confirmed yet another exotic prediction, showing that spacetime responds not just to mass, but to mass in motion. The precision of modern tests has reached astonishing levels. Lunar laser ranging, which bounces light off mirrors left on the Moon by Apollo astronauts, tests general relativity to parts in 10 trillion. Atomic clocks compared across different altitudes confirm gravitational time dilation to similar precision. Observations of pulsars, rapidly spinning neutron stars emitting regular radio pulses, test relativistic effects in strong gravitational fields. Binary pulsar systems continue providing laboratories where orbital dynamics can be measured with phenomenal accuracy. Every measurement strengthens the evidence that spacetime curvature correctly describes gravity across vast ranges of scale and intensity. What makes these detections so powerful is how they probe different aspects of general relativity. LIGO tests the theory's predictions about dynamic, radiating spacetime in the strongest gravitational fields outside black hole horizons. The Event Horizon Telescope examines stationary black holes and the geometry immediately surrounding them. Gravity Probe B measures subtle rotational effects in weak gravity. Lunar ranging tests the theory in the relatively gentle environment of the Earth-Moon system. Pulsar timing explores intermediate strength fields with extraordinary timing precision. Together, these experiments span more than 12 orders of magnitude in gravitational field strength and test general relativity under wildly different conditions. The consistent agreement across such diverse regimes demonstrates that Einstein's geometric framework captures something deeply true about reality. Spacetime is not a convenient mathematical abstraction. It is a physical structure that waves, curves, twists, and responds to matter exactly as the equations predict. We have heard it ripple, seen its shadows, measured its twisting, and confirmed its predictions to staggering precision. Yet all this success still leaves fundamental questions unanswered about what spacetime actually is beneath the mathematical surface. Why does your ability to navigate to an unfamiliar restaurant depend on equations describing warped geometry near massive objects? Modern civilization runs on technologies that would fail completely if spacetime remained flat and absolute as common sense suggests. Every time you check your location on a mapping application, request directions to a destination, or track a delivery vehicle, you're relying on satellites that experience time differently than you do because they orbit in a weaker gravitational field while simultaneously moving at tremendous velocity. The Global Positioning System operates by comparing arrival times of radio signals broadcast from at least 4 satellites simultaneously. Each satellite transmits a timestamp indicating exactly when the signal left, and your receiver calculates how long each signal took to arrive by comparing broadcast times with reception time, multiplying travel duration by light. Speed gives distance to each satellite, and triangulating from multiple distances determines your position. This sounds straightforward until you realize that timing errors of even 1 microsecond translate to position errors of 300 meters because electromagnetic radiation covers that much ground in a millionth of a second. GPS requires nanosecond precision, and at that scale relativity becomes essential. Satellites orbit at approximately 20,000 kilometers altitude, traveling near 14,000 kilometers per hour. Special relativity predicts that moving clocks tick slower, causing satellite clocks to lose about 7 microseconds daily compared to ground clocks. General relativity predicts that clocks in weaker gravity tick faster, causing satellite clocks to gain approximately 45 microseconds daily. The net effect means satellite clocks run 38 microseconds faster per day than identical clocks on Earth's surface. Without corrections, position calculations would accumulate errors exceeding 10 kilometers within a single day. Engineers compensate by programming satellite clocks to tick at slightly different rates before launch, adjusting their frequency so that once in orbit, accounting for both velocity and gravitational effects, they synchronize perfectly with ground time. Every successful navigation confirms that spacetime curves exactly as Einstein described. Particle accelerators provide another domain where relativistic effects dominate engineering. When physicists accelerate protons or electrons to speeds approaching light velocity, the particle's behavior deviates dramatically from classical predictions. As velocity increases, the energy required to accelerate further grows without limit, not because of frictional resistance, but because the relationship between energy and momentum changes at relativistic speeds. Particles approaching light velocity become harder to accelerate, behaving as though their inertia increases. The Large Hadron Collider accelerates protons to 99.999991% of light speed, at which point each proton carries as much kinetic energy as a flying mosquito despite having 1,000,000 billion times less mass. Classical physics cannot account for this energy concentration. Only by incorporating special relativity's energy momentum relationship do calculations match observed particle behavior. The accelerator's magnetic fields must be precisely calibrated to bend these ultra-fast particles along the desired path, and those calibrations depend entirely on relativistic formulas. If engineers use Newtonian mechanics, the particles would smash into the accelerator walls within moments. Satellite communications similarly require relativistic adjustments. Geostationary satellites orbit at altitudes near 36,000 kilometers, maintaining fixed positions relative to Earth's surface by matching the planet's rotation period. These satellites experience even stronger gravitational time dilation than GPS satellites while moving more slowly through space. Communication systems, timing signals between ground stations and satellites must account for the fact that clocks aboard satellites tick faster than ground clocks. Television broadcasts, internet traffic, and telephone calls routed through satellites all depend on systems engineered with general relativity built into their timing protocols. Cosmology, the study of the universe's large-scale structure and evolution, relies entirely on general relativity to make sense of observations. When astronomers measure how quickly distant galaxies recede, they find velocities proportional to distance, indicating the universe expands uniformly. General relativity provides the framework for understanding this expansion, not as galaxies moving through static space, but as space itself stretching, carrying galaxies along. The equations governing cosmic expansion lead to specific predictions about how expansion rate changes over time, depending on the universe's matter and energy content. Observations of distant supernovae, cosmic microwave background radiation, and large-scale galaxy distributions all fit models derived from Einstein's field equations applied to the entire cosmos. These cosmological models predict phenomena like gravitational lensing, where massive galaxy clusters bend light from background objects, creating multiple distorted images. They predict the existence of cosmic microwave background radiation, the cooled remnant of early universe heat. They predict specific patterns in how galaxies cluster based on tiny density fluctuations in the early universe, amplified by gravity over billions of years. Every cosmological observation confirms predictions flowing from curved spacetime dynamics on the largest scales imaginable. What makes these technological successes so intriguing is how they transform abstract mathematics into practical necessity. General relativity began as pure theory, Einstein working out field equations with no applications in mind. A century later, devices in billions of pockets depend on those equations being precisely correct. Navigation, communication, particle physics research, and cosmological understanding all require space-time curvature. These aren't approximations or convenience. The technology literally fails without relativistic corrections, yet this very success deepens the mystery of what space-time fundamentally is. We can engineer with its properties, predict its behavior, and confirm its curvature to extraordinary precision. We've built a civilization partially dependent on understanding how mass warps geometry and how motion affects temporal flow. GPS works, particle accelerators function, satellites communicate, cosmological models match observations. All this practical triumph demonstrates that space-time curvature describes reality accurately, but describing accurately differs from understanding deeply. Knowing that space-time curves doesn't explain what curves or why curvature produces effects we call gravitational. Calculating time dilation precisely doesn't reveal why time is something that can dilate. Predicting gravitational waves doesn't illuminate what medium waves or whether calling it a medium even makes sense. Engineers can use relativity without grasping its ultimate nature. The equations deliver correct answers whether or not we comprehend what they're really telling us about reality's foundations. This creates an odd situation where our most precisely tested physics also harbours the deepest conceptual mysteries. We've turned spacetime into technology, confirming it billions of times daily through working devices, yet we still argue about whether it's fundamentally real or emergent, substance or geometry, physical or mathematical. Success in application doesn't guarantee success in interpretation. The universe allows us to use spacetime's properties while keeping its essence mysterious, offering practical mastery without philosophical clarity. What happens when the two most successful theories in physics history meet each other in the same location, and why do they refuse to cooperate? For nearly a century, physicists have lived with an uncomfortable division at the heart of their understanding. Quantum mechanics describes the microscopic realm with astonishing precision, predicting atomic spectra, chemical bonds, semiconductor behavior, and particle interactions with accuracy that reaches parts per billion in some cases. General relativity describes gravity and cosmic structure with equal success, matching observations from planetary orbits to colliding black holes. Each theory reigns supreme within its territory. Quantum mechanics handles electrons, photons, quarks, and the forces binding them together. General relativity handles planets, stars, galaxies, and the curved geometry governing their motions. Problems arise only when you ask what happens in situations where both theories should matter simultaneously, where gravitational effects become strong at quantum scales, or quantum effects become important in gravitational contexts. These situations sound rare and abstract, easy to dismiss as extreme edge cases, and they represent real physical conditions. The center of a black hole is one such place. Every bit of matter that crosses the event horizon gets crushed toward a central singularity, where density theoretically becomes infinite and space-time curvature grows without bound. General relativity predicts this singularity, but cannot describe what actually happens there, because its equations produce nonsensical infinities. Quantum mechanics should step in at tiny scales to prevent infinite compression, but quantum mechanics assumes space-time is a fixed background stage, not something that curves and flexes. The two frameworks give contradictory instructions. Another location where both theories should apply is the universe's beginning. Trace cosmic expansion backward, and you reach a moment when all matter and energy occupied an infinitesimally small volume at incredibly high density. General relativity describes the expansion accurately once the universe grew large enough, but in the first moments, quantum effects dominated everything. The Big Bang should be a quantum gravitational event, yet we have no consistent theory combining these aspects. Every attempt to describe the initial state requires assumptions that mix quantum and gravitational ideas in ways that don't fit together cleanly. The root of the conflict lies in fundamentally different assumptions each theory makes about reality's structure. Quantum mechanics treats particles and fields as fundamentally uncertain, existing in superpositions of multiple states until measurement forces them into definite configurations. Position and momentum cannot both be precisely known. Energy and time obey similar uncertainty relations. Everything at small scales becomes probabilistic, governed by wave functions that spread and interfere. General relativity treats spacetime as smooth, continuous geometry described by precise curvature at every point. Mass and energy curve spacetime in specific deterministic ways. Trajectories through curved spacetime follow definite paths called geodesics. There's no uncertainty in the geometry itself, no probability clouds describing where spacetime might be curved versus flat. When you try combining these pictures, contradictions multiply. Quantum mechanics requires knowing exact positions and times to define fields and particles, but general relativity says spacetime itself fluctuates and curves. How can you define a particle's position precisely if the geometry defining position is uncertain? General relativity needs smooth, continuous spacetime to calculate curvature, but quantum mechanics suggests everything becomes grainy and probabilistic at small scales. Can geometry be both smooth and quantized? The conflict crystallizes at the Planck scale, named after Max Planck, who first identified fundamental constants underlying quantum behavior. By combining the speed of light, Newton's gravitational constant, and Planck's constant from quantum mechanics, you can construct natural units of length, time, and energy. The Planck length equals approximately 1.6 times 10 to the minus 35 meters, roughly 20 orders of magnitude smaller than a proton. The Planck time, the duration light takes to cross one Planck length, equals about 5.4 times 10 to the minus 44 seconds. These aren't arbitrary choices. They represent scales where quantum gravitational effects should become unavoidable. At the Planck length, quantum uncertainty in position becomes comparable to the wavelength of gravitational effects you're trying to measure. Attempting to probe distances smaller than the Planck length requires concentrating so much energy in such a tiny region that you create a black hole, making further measurement impossible. The Planck scale marks a fundamental barrier where conventional notions of spacetime likely break down. Below this threshold, the smooth geometry of general relativity probably gives way to something discrete, foamy, or altogether different. Quantum fluctuations in geometry itself should dominate, creating a landscape where asking about specific positions or times loses meaning. Yet neither quantum mechanics nor general relativity can describe this regime. Quantum mechanics doesn't know how to handle curved, dynamic spacetime. General relativity doesn't include quantum uncertainty in its geometric structure. Physicists have attempted numerous strategies to merge these frameworks. Some try quantizing gravity by treating gravitational fields like other quantum fields, carried by particles called gravitons. This approach works initially for weak gravity but produces uncontrollable infinities when gravitational interactions become strong. Unlike other quantum field theories where infinities can be systematically removed through renormalization, quantum gravity's infinities resist all techniques. The mathematics simply fails to produce sensible finite answers. Other approaches suggest spacetime itself might not be fundamental but emergent, arising from more basic quantum ingredients the way temperature emerges from molecular motion. If spacetime is not the deepest level of reality, perhaps the conflict dissolves because we're asking the wrong question, trying to combine things that exist at different levels of description. These ideas remain speculative, lacking definitive experimental tests because the Planck scale lies far beyond current technology's reach. What makes this situation particularly frustrating is that we're not missing minor details or small corrections. The disconnect between quantum mechanics and general relativity represents a chasm in our understanding of nature's foundations. We have two spectacularly successful theories that together describe essentially everything we can observe, yet they cannot coexist in situations where both should apply. It's as though we have two languages, each perfectly suited to describing different aspects of reality, but lacking any translation dictionary between them. You can speak fluent quantum or fluent relativity, but not both simultaneously. This isn't a sign that either theory is wrong. Both are correct within their domains. It suggests instead that there are approximations to some deeper theory we haven't discovered, pieces of a larger framework that reduces to quantum mechanics in one limit and general relativity in another. Uncovering that underlying theory represents one of physics' greatest challenges, made harder by the fact that the scale where the answer matters most lies beyond experimental access. Why does merging quantum mechanics with general relativity produce mathematical nonsense instead of deeper insight? The fundamental obstacle stems from each theory requiring conditions the other explicitly denies. Quantum field theory, the framework describing electromagnetic, weak and strong forces, assumes particles and fields exist within a fixed spacetime backdrop. Fields oscillate and particles move through this stage, but the stage itself remains stable and unchanging. Calculations rely on this fixed geometry to define what happens at specific locations and moments. You cannot compute quantum probabilities without established coordinates telling you where and when events occur. General relativity demolishes this assumption entirely. Spacetime is not a fixed arena, but a dynamic participant that bends, flexes, and responds to whatever occupies it. Mass curves geometry, and that curvature determines how objects move. The stage itself becomes part of the performance, shifting in response to actors upon it. When quantum physics meets this dynamic geometry, the mathematical machinery grinding to a halt. Attempts at quantizing gravity by treating it like other forces initially appear promising. Physicists imagine gravitons, hypothetical particles carrying gravitational interactions the way photons carry electromagnetic force. At weak field strengths, this approach yields sensible predictions. Problems emerge when interactions become strong or occur at short distances, where quantum effects intensify. Calculations produce infinities that resist every technique developed for taming similar problems in other quantum theories. Normally, quantum field calculations generate infinite quantities that can be systematically absorbed into redefined parameters through renormalization. This mathematical procedure has worked brilliantly for electromagnetism and nuclear forces, removing infinities while preserving predictive power. Gravity refuses to cooperate. The infinities multiply faster than they can be controlled. Each attempt to remove one infinity spawns new ones in an endless cascade. The theory becomes non-renormalizable, a technical term meaning the mathematics breaks irreparably. No finite number of adjustments can produce meaningful predictions at high energies or short distances. This failure signals something profound rather than a mere calculational difficulty. It suggests that treating gravity as just another quantum force fundamentally misunderstands its nature. Gravity is geometry itself, not something happening within geometry. Asking what quantum geometry means requires rethinking space and time at their foundations. The conflict resembles trying to translate between languages lacking common concepts. Quantum mechanics speaks in probabilities, uncertainties, and discrete states. General relativity speaks in smooth curves, deterministic evolution, and continuous fields. Neither vocabulary contains words for expressing ideas natural to the other. Quantum theory has no term for dynamic geometry. Relativity has no expression for intrinsic uncertainty in space-time structure. This isn't ignorance or incomplete development. Both theories are internally consistent and empirically validated within their domains. The problem arises precisely because they're so successful on their own terms that forcing them together violates principles each holds essential. Quantum mechanics cannot abandon fixed backgrounds without losing its ability to define measurements. General relativity cannot treat spacetime as static without contradicting its central insight that geometry responds to content. Some physicists argue this deadlock means spacetime itself is not fundamental, but emerges from deeper quantum processes. If geometry arises from underlying quantum entanglement or information patterns, perhaps the conflict dissolves because we're trying to quantize something that's already quantum at a more basic level. Others suggest entirely new mathematical frameworks beyond both current theories. String theory replaces point particles with vibrating strings, smoothing out the short-distance singularities that cause infinities. Loop quantum gravity quantizes geometry directly, making spacetime discrete rather than continuous at the smallest scales. Each approach requires abandoning assumptions so basic they seem inseparable from physics itself. Despite decades of effort, no proposal has achieved what quantizing electromagnetism accomplished: a consistent framework matching all observations while revealing new testable predictions. The mathematics of quantum gravity remains stubbornly broken, a jigsaw where pieces from different puzzles have been forced together. We're left with two magnificent theories describing different aspects of one universe, unable to speak coherently about situations where both should apply simultaneously. Where in our actual universe do quantum mechanics and general relativity crash into each other with such force that neither theory can describe what's happening? These aren't hypothetical thought experiments or abstract mathematical scenarios. They're real physical locations and moments that definitely exist or existed, yet remain fundamentally mysterious because our best theories fail simultaneously at describing them. The most dramatic example sits at the heart of every black hole. Once matter crosses the event horizon, general relativity predicts inevitable collapse toward a central singularity where density becomes infinite and space-time curvature grows without limit. The equations themselves break down, producing mathematical infinities that signal the theory has reached its boundary. Yet something real must occur at that location. Matter doesn't simply vanish or stop existing. Quantum mechanics should prevent infinite compression by introducing uncertainty that spreads matter across a small but finite region. But quantum theory cannot operate in wildly fluctuating geometry, where the very notion of position becomes ambiguous. We know singularities form because black holes definitely exist, confirmed through gravitational wave detections and direct imaging, yet we cannot describe their cause. An equally mysterious moment lies in cosmic history's opening instant. Trace the universe's expansion backward through time, and you approach a state of extreme density and temperature existing roughly 13.8 billion years ago. General relativity describes the expansion beautifully once the cosmos grew beyond subatomic dimensions, but the very first fraction of a second requires quantum gravity. The universe at 10 to the minus 43 seconds after its beginning occupied a volume near the Planck scale where quantum fluctuations in geometry itself dominated. Every bit of matter and energy we see today was compressed into a region smaller than a proton, with densities and curvatures where both quantum uncertainty and gravitational effects were equally important. This initial moment determined everything that followed. The universe's expansion rate, matter distribution, even the laws of physics as temperature dropped, yet we have no complete theory describing it. The early universe wasn't hypothetical. It happened. We just cannot explain how. Even in empty space, quantum mechanics predicts constant fluctuations where particle pairs briefly appear and disappear, borrowing energy from vacuum uncertainty. At the Planck scale, similar fluctuations should affect spacetime geometry itself. Tiny regions of space might momentarily curve intensely or even pinch off into microscopic wormholes before dissolving. This quantum foam represents spacetime's intrinsic jitteriness at the smallest scales, but calculating its properties requires a theory unifying quantum and gravitational physics. We suspect it exists based on theoretical consistency, yet cannot describe it quantitatively. Information paradoxes present another domain where both theories must apply, but conflict. When matter falls into a black hole, quantum mechanics insists the information describing that matter's quantum state cannot be destroyed, only scrambled or transformed. General relativity suggests information disappears behind the event horizon, lost forever as the singularity forms. Hawking radiation, a quantum effect near horizons, slowly evaporates black holes over immense timescales. If information isn't encoded in this radiation, it vanishes when the hole finally disappears, violating quantum principles. If information does escape, the mechanism requires quantum processes in strongly curved spacetime that neither theory alone can adequately describe. This isn't abstract philosophy. Real black holes evaporate, and the information they contain must go somewhere, or quantum mechanics fails. Colliding neutron stars provide another laboratory where quantum and gravitational physics intertwine. In the instant before merger, matter reaches nuclear densities while experiencing gravitational fields approaching black hole strength. The equation of state describing how matter behaves under these conditions requires understanding quantum chromodynamics in extreme spacetime curvature. Gravitational wave signals encode information about this physics, but extracting it needs models that properly combine both frameworks. Each of these situations represents genuine physical reality, where spacetime curvature is intense and quantum effects are unavoidable. They are not edge cases we can safely ignore. They're windows into regimes where nature definitely operates under rules we haven't fully grasped. The universe doesn't care that our theories are incomplete. It functioned perfectly well during its quantum gravitational birth and continues harboring black hole singularities whether or not we can describe them. Our ignorance doesn't make these places disappear. It simply leaves them shrouded in mystery, despite being as real as anything else. Could the smooth fabric of space-time actually be woven from discrete threads too tiny to detect, like a photograph that looks continuous until you zoom in far enough to see individual pixels? For over a century, general relativity has treated space-time as infinitely divisible, a continuous manifold where you can always imagine smaller distances and briefer durations without hitting any fundamental limit. This classical picture envisions geometry as perfectly smooth, describable by functions that vary continuously from point to point without gaps or jumps. Curvature changes gradually. Distances can take any value whatsoever. Time flows in an unbroken stream. Yet every other aspect of physics revealed through 20th century discoveries turned out to be quantized, coming in discrete lumps rather than continuous distributions. Energy arrives in photon packets. Electric charge exists in multiples of the electron's charge. Angular momentum takes specific quantized values. Even fields that appear smooth are built from particle excitations with definite energies. This pattern suggests spacetime itself might similarly be granular at sufficiently tiny scales, composed of fundamental units that cannot be further subdivided. Loop quantum gravity pursues this idea directly by applying quantization procedures to geometry itself. Rather than treating spacetime as a background, the approach builds it from networks of quantum relationships. Space emerges from nodes connected by links, each link representing a quantum of area or volume. These networks evolve and reconfigure, but always in discrete steps. Area and volume become quantized just as energy is, with minimum possible values set by combinations of fundamental constants. The Planck length, roughly 10 to the minus 35 meters, appears naturally as the scale where this graininess manifests. At distances larger than Planck scale, the discrete structure averages out to appear smooth, just as a beach looks uniform from afar despite being made of individual sand grains. Loop quantum gravity eliminates singularities by preventing infinite compression as matter collapses. It reaches densities where quantum geometric effects halt further contraction, potentially causing a bounce rather than forming a true singularity. This framework offers mathematical consistency and removes some infinities plaguing other approaches, but struggles to recover general relativity's predictions at larger scales and lacks clear experimental tests. String theory takes a completely different path by proposing that fundamental entities are not point particles, but tiny vibrating strings. Different vibration patterns produce different particles. One particular vibration mode behaves exactly like a graviton, the hypothetical quantum of gravity, making gravity's emergence natural within the framework. However, mathematical consistency requires strings to vibrate in 10 or 11 dimensions, rather than the familiar 4. The extra dimensions must be compactified, curled up so tightly they remain undetectable at accessible energies. In this picture, space-time isn't fundamental at all. The familiar 4 dimensions emerge from the dynamics of strings moving through higher dimensional space. What we perceive as smooth geometry arises from collective string behavior, much as temperature emerges from molecular motion without individual molecules possessing temperature. String theory unifies all forces and particles within one mathematical structure, but requires accepting dimensions beyond direct observation and makes few testable predictions at experimentally accessible energies. Both approaches suggest spacetime may not be the deepest level of reality. Whether geometry is discrete networks or emergent from string dynamics, the smooth fabric we experience could be an approximation valid for everyday scales, but breaking down at Planck dimensions. This possibility fundamentally alters what it means to ask what spacetime is made of. If geometry itself is constructed from more basic elements, quantum or stringy, then space and time are products rather than ingredients. Deciding between these visions or discovering an entirely different answer requires evidence currently beyond reach. The Planck scale where answers hide sits roughly 20 orders of magnitude below the smallest distances probed by particle accelerators. Testing whether spacetime is truly continuous or secretly grainy demands energies nature may not have produced since the universe's first instant. We're left with mathematically consistent possibilities pointing in different directions, each suggesting spacetime's familiar smoothness conceals deeper structure we've barely begun to glimpse. What if everything you perceive as three-dimensional space, including depth, volume, and the ability to move forward and backward, is actually encoded on a distant two-dimensional surface like a hologram projecting apparent thickness? This bizarre possibility emerged from studying black hole thermodynamics in the 1970s. When physicists calculated the entropy of a black hole, expecting it to scale with volume as it does for ordinary objects, they discovered something profoundly strange. Black hole entropy is proportional to the event horizon's surface area, not the volume enclosed within. A black hole twice the radius has 4 times the area and 4 times the entropy, suggesting all information about its contents is somehow stored on the boundary rather than throughout the interior. This violated intuitions about how information storage works. Normally, the amount of data you can pack into a region grows with its volume. Libraries hold more books than pamphlets because they offer more three-dimensional space. Computer hard drives store information throughout their bulk. Yet black holes, the densest possible information repositories, encode everything on their two-dimensional surfaces. Jacob Bekenstein and Stephen Hawking formalized this relationship, showing the maximum entropy any region can contain equals its boundary area measured in Planck units divided by 4. This holographic bound suggests the universe itself might work similarly, with three-dimensional reality emerging from information fundamentally encoded on a distant two-dimensional boundary. The idea gained mathematical support from an unexpected discovery in string theory. Juan Maldacena found a precise correspondence between gravitational physics in a particular curved spacetime and quantum field theory living on that spacetime's boundary. This anti-de sitter conformal field theory correspondence, often abbreviated ADS-CFT, demonstrates that a theory with gravity in 5 dimensions perfectly matches a quantum theory without gravity in 4 dimensions. Every phenomenon in the higher dimensional gravitational theory corresponds exactly to some process in the lower dimensional quantum theory. There are different descriptions of the same physics, related like a hologram and its projection. What appears as particles moving through curved spacetime in one description emerges as quantum field excitations on a boundary in the other. Neither description is more fundamental. They are dual perspectives on one underlying reality. If this correspondence extends beyond the specific mathematical example where it was proven, it suggests our familiar spacetime might similarly emerge from quantum information living on a distant boundary. The 3 dimensions we move through, the volume we occupy, perhaps even time itself, could be holographic projections of data encoded elsewhere. This doesn't mean reality is an illusion or simulation. It means the dimensionality we experience might not reflect the deepest level of description. Just as temperature is real despite emerging from molecular motion, spacetime could be genuine while arising from boundary information. Several lines of evidence support this radical restructuring. Black hole information paradoxes become more tractable in holographic frameworks because information never truly enters the black hole's interior, but remains encoded on the horizon. Quantum entanglement patterns between regions exhibit properties consistent with geometric connections in a holographic dual, suggesting space itself might emerge from entanglement structure. Some calculations of quantum corrections to gravitational physics work more cleanly when formulated holographically, hinting that the boundary description captures something fundamental that the bulk geometric description obscures. If spacetime is holographic, what does this mean for reality's nature? It suggests geometry is not the most basic ingredient but a derived concept. Useful for describing physics at human scales, but potentially misleading when asking ultimate questions. Space and time would be emergent phenomena, appearing only when looking at certain collective behaviors of boundary information. Asking what spacetime is made of would be like asking what temperature is made of. The question reveals a category error, mistaking an emergent property for a fundamental constituent. This possibility remains controversial and unproven beyond specific mathematical examples. Extending holography to our actual universe faces technical obstacles and conceptual puzzles. Where is the boundary encoding our reality? Does the holographic description require a boundary at spatial infinity, or does it work differently in cosmological settings? Despite uncertainties, holography represents one of the most profound shifts in how physicists think about spacetime, transforming it from fundamental arena to emergent projection. Could the geometry connecting 2 distant points in space actually be built from the quantum entanglement linking particles at those locations, making geometry and entanglement 2 sides of the same phenomenon? This startling possibility treats spacetime not as a fundamental ingredient, but as an emergent structure arising from deeper quantum relationships, similar to how temperature emerges from molecular motion without molecules themselves possessing temperature. When atoms move rapidly in random directions, their collective behavior produces what we measure as heat. Yet no individual atom is hot or cold. Perhaps spacetime works similarly, appearing only when quantum systems become sufficiently complex and entangled, with geometry reflecting the pattern and strength of quantum correlations between regions. Mark van Raamsdonk demonstrated that entanglement entropy, a measure of quantum correlations between separated regions, relates directly to geometric properties in holographic theories. Removing entanglement tears spacetime apart. Strong entanglement creates robust geometric connections. This suggests spacetime's very existence depends on quantum information being shared between locations. Without entanglement, there might be no space connecting points, no distance separating them, no geometric relationship whatsoever. The conjecture known as ER equals EPR makes this connection even more explicit. Einstein-Rosenstein. Bridges, commonly called wormholes, are geometric connections linking distant regions through curved spacetime. Einstein-Podolsky-Rosen pairs are quantum entangled particles sharing correlations regardless of separation. The conjecture proposes these apparently different phenomena are actually identical. Every pair of entangled particles is connected by a microscopic wormhole. Every wormhole represents maximal entanglement between its mouths. Geometry and quantum correlation become 2 languages describing the same underlying reality. If true, this means spacetime's fabric is literally woven from quantum entanglement. with distance emerging from entanglement strength and connectivity arising from correlation patterns. Building on these ideas, researchers explored whether spacetime could emerge from quantum error correction, the same mathematics protecting quantum information in quantum computers. Error-correcting codes store information redundantly so that corrupting some bits doesn't destroy the encoded data. Certain codes exhibit geometric properties where logical operations on encoded information correspond to movements through an emergent space. The code structure defines distance, connectivity, and even causal relationships. Extending these toy models suggests our spacetime might similarly be a code, with physical laws emerging as error correction protocols preserving quantum information against corruption. Particles moving through space would correspond to information propagating through the code structure. Gravity curving geometry would reflect how the code responds to concentrated information. This framework remains highly speculative, but offers tantalizing hints that spacetime's geometric properties might not be fundamental, but instead derive from information theoretic principles. If spacetime genuinely emerges from entanglement, quantum codes, or related structures, what lies beneath? What are the fundamental building blocks from which geometry arises? Different proposals offer varying answers. Some suggest pure quantum information without any geometric interpretation at the deepest level. Others propose networks of discrete quantum events related by causal rather than spatial connections. Certain approaches imagine quantum fields defined without reference to spacetime, with geometry appearing only as a convenient description of field correlations. Each framework attempts to identify something more primitive than space and time, something that exists independently of geometric notions, from which familiar spacetime emerges when appropriate conditions are met. This emergence would be automatic, not requiring fine-tuning or special initial conditions, arising inevitably from underlying quantum dynamics. Temperature doesn't need careful adjustment to appear. It emerges naturally whenever many particles interact. Similarly, spacetime might emerge unavoidably from quantum entanglement networks above certain complexity thresholds. Below that threshold, asking about distance or duration would be meaningless, like asking the temperature of a single atom. The familiar classical spacetime we inhabit would represent a thermodynamic limit, valid for describing large numbers of entangled quantum degrees of freedom, but breaking down at small scales where the discrete quantum substrate becomes apparent. Testing these ideas faces enormous challenges because the emergence happens at scales inaccessible to experiments. Yet certain signatures might appear in precision cosmological observations or particle physics measurements if spacetime truly is emergent rather than fundamental. The very existence of a minimum length scale, subtle violations of Lorentz invariance at extreme energies, or particular patterns in quantum gravity corrections could all hint at underlying structure. For now, emergent spacetime remains a compelling theoretical possibility, reshaping how physicists think about reality's foundations without definitive empirical confirmation. What would spacetime look like if you could zoom in far enough to see its smallest possible structure? And why does the very act of looking that closely destroy what you're trying to observe? At scales humans can perceive or instruments can probe, spacetime appears beautifully smooth, a continuous manifold where distances vary gradually and geometry changes in predictable ways. Descend toward the Planck length, however roughly 10 to the minus 35 meters, and this smooth picture dissolves into something radically different. Quantum mechanics insists that uncertainty increases as you examine smaller scales. Position, momentum cannot both be precisely known. Energy and time obey similar restrictions. These uncertainties normally affect particles and fields while leaving the spacetime stage itself unaltered, but at Planck dimensions, fluctuations become so violent they affect geometry itself. Spacetime stops being a passive arena and becomes an active participant in quantum uncertainty. John Wheeler coined the term quantum foam to describe this regime where geometry fluctuates wildly. Imagine zooming into what appears as flat, empty space. As magnification increases, tiny ripples emerge, then larger distortions, until finally the very notion of smooth surface disappears into a seething froth of constantly changing curvature. Regions of spacetime curve intensely for brief instants before relaxing. Microscopic wormholes might spontaneously open and close. Virtual black holes Tiny gravitational knots far smaller than atomic nuclei could flash into existence and evaporate before leaving detectable traces. None of this violates conservation laws because these fluctuations borrow energy from quantum uncertainty over timescales too brief for the debt to matter. The foam isn't chaotic randomness but structured uncertainty, governed by quantum principles applied to geometry itself rather than matter within geometry. At these scales, asking about the precise distance between 2 points becomes meaningless because distance itself fluctuates. Attempting to measure separation requires probes with wavelengths comparable to the scale being examined. Shorter wavelengths demand higher energy. Concentrating enough energy to probe Planck-length distances creates gravitational fields so intense they curve spacetime dramatically, forming microscopic black holes that swallow the very information you hope to extract. The measurement destroys what you're measuring. This isn't technological limitation but fundamental physics. The Planck length represents an absolute barrier beyond which conventional notions of distance break down. You cannot build a ruler shorter than Planck length because the ruler itself would collapse into a black hole. You cannot measure durations briefer than Planck time because doing so requires energy concentrations that warp temporal flow beyond recognition. These aren't practical obstacles awaiting better instruments but intrinsic features of quantum gravity. Spacetime has minimum resolvable features below which measurement becomes self-defeating. Some theorists interpret quantum foam as indicating spacetime's discrete nature, suggesting geometry is quantized like energy, coming in minimum chunks rather than varying continuously. Others view it as signaling spacetime's emergence from non-geometric quantum substrate. Still others argue foam represents our ignorance, artifacts of applying quantum mechanics and general relativity beyond their valid domains, rather than genuine physical phenomena. Without a complete quantum gravity theory, we cannot definitively describe Planck-scale physics. What remains clear is that smooth continuous spacetime, the foundation of general relativity, and our everyday geometric intuitions, represents an approximation valid only above certain scales. Below Planck dimensions, whatever exists cannot be described using familiar concepts like distance, duration, or even space and time themselves. The foam, whether real fluctuating geometry or metaphor for our theoretical gaps, marks the frontier where known physics ends and mystery begins, where space-time as we conceive it dissolves into something we lack the mathematics and perhaps even the conceptual vocabulary to properly describe. Could the universe's birth have been not an explosive beginning from nothing, but a bounce from a previous contracting phase? And why does answering this question require understanding physics we haven't yet discovered? General relativity, when applied to an expanding universe, predicts that tracing cosmic evolution backward leads inevitably to a singularity. At this initial point, density and temperature become infinite, space-time curvature grows without bound, and the equations themselves break down. This Big Bang singularity represents the ultimate mystery, a moment where mathematical description fails completely. Classical physics offers no mechanism to prevent collapse to infinite density. Every trajectory through curved space-time, when followed sufficiently far into the past, terminates at a point where prediction becomes impossible. Yet quantum mechanics fundamentally opposes infinities. Heisenberg uncertainty prevents confining particles to infinitely precise positions. Quantum fields resist infinite energy concentrations. The probabilistic nature of quantum processes suggests some mechanism should halt collapse before density becomes truly infinite, replacing the singularity with something finite, though perhaps extraordinarily dense. Determining what actually occurred requires quantum gravity, the missing theory combining quantum mechanics with curved spacetime. Without it, physicists can describe the universe from microseconds after its beginning, but not the beginning itself. Loop quantum cosmology, an application of loop quantum gravity to the early universe, offers one possible resolution. In this framework, geometry becomes discrete at Planck scales. As matter contracts, quantum geometric effects introduce a repulsive force growing stronger at extreme densities. Rather than collapsing indefinitely, the universe reaches a maximum density then rebounds. The Big Bang becomes a big bounce, a transition point where a previous contracting phase reversed into our current expansion. Before the bounce lies an earlier cosmic epoch, perhaps similar to ours or radically different depending on conditions at turnaround. This scenario eliminates the singularity by preventing infinite compression, though it introduces new questions. What determined conditions before the bounce? Could bounces repeat indefinitely, creating an eternal cyclic cosmos? How much information survives the bounce to influence our current expansion phase? Loop quantum cosmology makes specific predictions about density limits and bounce dynamics, but these occur at energies far beyond experimental verification. Other quantum gravity approaches suggest different possibilities. Some string theory scenarios propose the universe emerged from colliding higher dimensional membranes. Certain models invoke quantum tunneling from nothing, where space-time itself fluctuates into existence without requiring prior cause or earlier phase. Causal set approaches suggest discrete space-time events accumulate gradually, rather than emerging from a singular beginning point. Each framework replaces classical singularity with different physics, none yet confirmed observationally. What remains consistent across approaches is that the first Planck time, roughly 10 to the minus 43 seconds, represents an impenetrable barrier given current understanding. During that initial period, quantum gravitational effects dominated completely. Space-time as we know it might not have existed in recognizable form. Asking what happened during the Planck epoch might be asking the wrong question, if temporal concepts themselves emerged only afterward. The cosmic microwave, background the earliest light we can observe directly, originated roughly 380,000 years after the beginning, long after quantum gravity ceased being relevant. Everything earlier must be inferred through theoretical extrapolation. We can trace processes backward with confidence until we reach energies where quantum and gravitational effects become comparable in strength. Beyond that threshold, extrapolation becomes speculation. The universe's true beginning remains mysterious not because data is lacking, but because the physics governing that moment is unknown. This ignorance is an embarrassing failure but honest acknowledgement of theory's limits. We've successfully described cosmic evolution across 13.8 billion years, from the first second onward, an extraordinary achievement. The final instant, the actual origin, requires physics we're still developing. Whether that moment was a bounce, a tunneling event, a membrane collision, or something entirely unanticipated depends on which quantum gravity theory, if any, correctly describes reality's deepest level. Why does tomorrow feel fundamentally different from yesterday, when the equations governing physics treat both directions through time almost identically? General relativity presents space-time as a four-dimensional geometric structure, where time functions mathematically, much like spatial dimensions. You can move forward or backward through space with equal ease, and relativity's field equations work equally well whether time runs forward or backward. In this block universe picture, past events exist just as solidly as present ones. Your 5th birthday party occupies a specific location in spacetime no less real than this current moment. Future events already exist in regions of spacetime you haven't reached yet. Nothing flows or becomes. Everything simply is, laid out across 4 dimensions like a landscape where different times are different places. This mathematical treatment conflicts profoundly with lived experience. You remember yesterday but not tomorrow, suggesting the past has different status than the future. Causes precede effects rather than following them. Broken eggs never spontaneously reassemble. Warmth flows from hot objects to cold ones, never the reverse without external work. Aging proceeds in one direction. Consciousness experiences a moving present moment, and now that advances relentlessly from what was toward what will be. These everyday observations suggest time has an arrow, a preferred direction distinguishing past from future in ways that spatial dimensions lack. You can face north or south with equal validity, but you cannot face yesterday with the same freedom you face tomorrow. The puzzle deepens when examining physical laws. Newton's mechanics work identically forward or backward through time. If you filmed planets orbiting and played the recording in reverse, the motion would still obey Newton's equations perfectly. The same holds for general relativity. Light cones, geodesics, and curvature behave consistently, whether time increases or decreases. Electromagnetism shows one tiny asymmetry in how certain particle interactions distinguish time directions, but this effect is far too weak to explain macroscopic irreversibility. Quantum mechanics treats time specially in measurement, with wave function collapse being irreversible, though the Schrödinger equation itself is time-symmetric. The mystery is that almost all fundamental physics is time reversible while everything we experience isn't. Eggs breaking, ice melting, gases expanding, living organisms aging, memories forming, all these processes proceed in one temporal direction and one only. The second law of thermodynamics codifies this asymmetry by stating entropy increases over time. Disorder grows, energy spreads, concentrated patterns dissipate. This statistical tendency provides a physical arrow, pointing from low entropy past toward high entropy future. Yet the second law itself emerges from time-symmetric microscopic laws through statistical arguments. Individual molecular collisions work the same forward or backward. Only when considering vast numbers of molecules does irreversibility appear. This raises a profound question. If underlying laws are symmetric, where does the asymmetry we observe originate? One answer points to initial conditions. The universe began in an extraordinarily low entropy state, highly organized with energy concentrated rather than dispersed. As the cosmos evolved, entropy increased, following statistical tendencies encoded in having many particles. The arrow of time emerges not from laws themselves, but from boundary conditions, from the peculiar fact that the Big Bang started the universe in a special configuration. Why the beginning was low entropy rather than maximum entropy remains unexplained. This past hypothesis solves the arrow problem by pushing it to cosmology. Another perspective suggests the psychological arrow. Our sense of time flowing derives from entropy increase. Memory formation requires recording information, which increases entropy. Cause and effect relationships depend on correlations spreading from localized events, another entropy increasing process. Consciousness might construct the feeling of temporal flow from observing entropy's growth, making our experience of time derivative rather than fundamental. In this view, Bloch universe is correct but incomplete. It describes spacetime's geometry without explaining why inhabitants perceive asymmetric time. These explanations remain unsatisfying to many because they treat time's arrow as emergent or illusory rather than fundamental. Yet relativity's equations and quantum mechanics offer no preferred direction. The mystery persists because our deepest physics describes a timeless landscape while our deepest experience insists time flows. Could the entire reason you experience time flowing forward be traced to the single unexplained fact about the universe's initial conditions 13 billion years ago? The second law of thermodynamics, stating that entropy increases in isolated systems, provides the only fundamental physical principle distinguishing past from future. When ice melts, entropy grows. When gases mix, disorder rises. When stars radiate energy into space, the cosmos becomes more homogeneous. Each process follows a gradient from organized configurations toward dispersed ones. This gradient defines a temporal arrow because low entropy states evolve toward high entropy futures but never reverse. Shattered glass doesn't spontaneously reassemble because the broken state has vastly more possible microscopic arrangements than the intact configuration. The universe explores available states randomly, and high entropy states dominate by sheer number. Walking backward through entropy, increase effectively walks backward through time. Yet here emerges a puzzle that spacetime theory cannot address. If entropy naturally increases, tracing the universe backward should lead toward progressively lower entropy. The Big Bang indeed represents an extraordinarily low entropy state, with matter and energy distributed far more uniformly and concentrated than they are today. This initial organization seems fine-tuned for producing the structure we observe. Stars, galaxies, and planets form precisely because the early cosmos wasn't already at maximum entropy. Gravitational clumping, nuclear fusion, and chemical complexity all depend on energy gradients created by starting in a special organized state. But why did the universe begin this way? The second law doesn't explain initial conditions. It describes how systems evolve from whatever configuration they start in. Beginning at low entropy rather than maximum disorder requires explanation because high entropy states are overwhelmingly more probable. Imagine shuffling a deck of cards. You expect random disorder, not perfect suit order, because random arrangements vastly outnumber organized ones. Similarly, the universe could have begun in maximum entropy with energy already evenly spread and no capacity for interesting evolution. Instead, it started organized, enabling the complexity cascade leading to stars, chemistry, life, and consciousness. This past hypothesis, that the Big Bang simply was low entropy without deeper explanation, feels unsatisfying. It treats the universe's most important feature as a brute fact, rather than something following from physical principles. Some cosmologists propose inflation, rapid early expansion, might explain initial smoothness by stretching quantum fluctuations into macroscopic uniformity. Yet inflation itself requires special starting conditions and doesn't fully resolve why entropy began low. Others suggest our observable universe is a fluctuation within an eternal multiverse mostly at equilibrium. Occasionally, random statistical variations create low entropy pockets where entropy can subsequently increase. We inhabit such a pocket because only they support observers. This anthropic reasoning explains why we see low entropy beginnings, but not why the multiverse exists or why its overall state permits fluctuations. String theory landscapes with countless possible vacuum states similarly invoke observer selection without explaining underlying structure. Each approach shifts the mystery without eliminating it. Roger Penrose proposed that gravitational degrees of freedom, particularly black hole formation, represent enormous entropy increase not initially present. The early universe's low-gravity entropy, with matter smoothly distributed rather than clumped into black holes, provides the gradient driving cosmic evolution. As structure forms and black holes accumulate, gravitational entropy grows dramatically, dwarfing other contributions. This links entropy increase specifically to spacetime curvature evolution, making time's arrow partially gravitational. Yet this still doesn't explain why gravity started in such a special state. Without understanding initial conditions, we cannot claim to understand time's directionality. The second law describes entropy's behavior given a starting point, but doesn't predict that starting point. Spacetime theory describes geometry's evolution, but doesn't explain why evolution began from smooth rather than maximally curved configurations. The arrow of time emerges from initial asymmetry we observe but cannot drive. This gap leaves time's flow somewhat mysterious. We know entropy increase produces irreversibility, and we measure that the early universe had low entropy, yet we cannot explain this cosmological fact from first principles. Time's arrow ultimately traces to boundary conditions set at the Big Bang, conditions that remain as puzzling as the singularity itself. Why does your consciousness insist that this moment is uniquely real and moving forward when physics suggests all moments exist equally across an unchanging four-dimensional landscape? Memory provides perhaps the clearest manifestation of temporal asymmetry in conscious experience. You recall breakfast this morning but cannot recall tomorrow's dinner. Memories form through physical processes that record information about past events, creating neural patterns and encoding what happened. These records accumulate in one temporal direction only, building a personal history extending backward but not forward. The very concept of memory assumes a distinction between earlier states that can be remembered and later states that cannot yet exist in recorded form. Without this asymmetry, remembering would be meaningless. Causation similarly flows in one direction through conscious experience. You decide to raise your arm, then the arm rises. Intentions precede actions. Choices lead to consequences. Dropping a glass causes it to shatter, never the reverse. This causal structure organizes how we navigate reality, predicting outcome from actions and inferring past events from present evidence. Physics offers no fundamental reason for this directionality. The equations governing muscle contractions, neural signals, and falling objects work equally well with time reversed. Yet experience never presents reversed causation. Effects always follow causes, a pattern so deeply embedded in thought that imagining otherwise requires deliberate effort. Perhaps most striking is the sense of now advancing through time. Consciousness seems to occupy a moving present moment, a knife edge between fixed past and open future. Yesterday feels finished and immutable. Tomorrow feels undecided and contingent. Right now feels special, the only moment genuinely happening. This psychological present appears to flow, carrying you from what was toward what will be at a steady, inexorable pace. You cannot slow or reverse this flow, it simply carries you forward, whether you attend to it or ignore it. Yet block universe physics denies any privileged present. Einstein's equations treat all moments democratically. Your birth, this current instant, and your eventual death all exist equally as regions of space-time. Nothing flows or becomes. The sensation of advancing through time would be, in this view, an illusion created by consciousness, a side effect of how memory and perception construct experience from timeless physical states. Neural processes that create the feeling of flow operate within the block, recording sequences of states that produce subjective passage despite nothing objectively changing. Some philosophers argue this makes temporal flow unreal, a psychological artifact rather than physical feature. Others insist that dismissing experience as illusory doesn't resolve the mystery of why consciousness produces this particular illusion. If block universe is correct, explaining why time feels like it flows becomes as important as explaining any other aspect of reality. The feeling itself is real, even if what it represents is not. Consciousness evolved in entropy, increasing environments where memory formation and causal reasoning provided survival advantages. Perhaps the psychological arrow is simply how beings embedded in thermodynamic gradients perceive their situation. We are patterns in the block universe that include memories of earlier patterns, creating the subjective impression of having moved through time. This explanation remains unsatisfying to many because it treats consciousness as epiphenomenal, a passive observer of timeless physics rather than something engaged with genuine temporal flow. Reconciling the timeless mathematics of spacetime with the flowing experience of time represents one of philosophy's most persistent challenges. Physics describes what is, a four-dimensional structure laid out eternally. Consciousness describes what becomes, a succession of moments where past solidifies and future opens. Neither description feels complete without the other. Knowing that all events coexist in spacetime doesn't eliminate the feeling that only now is real. Understanding entropy gradients explain memory's directionality doesn't dissolve the sense of moving forward. The psychological arrow remains as vivid and undeniable as any physical phenomenon, yet spacetime theory offers no place for it. This gap suggests either our physics is incomplete, missing something essential about temporal experience, or our psychology is misleading, constructing flow from static structure. Neither option fully satisfies, leaving the mystery of experience time unresolved despite a century of relativistic understanding. What invisible force is tearing the universe apart faster and faster, and why does it constitute nearly 70% of everything that exists yet remain completely mysterious? In 1929, Edwin Hubble measured distances to remote galaxies and discovered something extraordinary. These galaxies were receding from us, and the farther away they were, the faster they moved. This relationship between distance and velocity revealed that space itself expands, carrying galaxies along like raisins in rising bread dough. Einstein's field equations, when applied to the universe as a whole, naturally produce either expansion or contraction depending on matter. Content. For decades, astronomers assumed this expansion should be slowing as gravity pulls matter together, gradually decelerating the outward motion initiated at the Big Bang. Observations through the late 20th century aimed to measure this deceleration rate, expecting to find cosmic expansion gradually weakening over billions of years. Then in 1998, two independent research teams studying distant supernovae discovered something nobody anticipated. These stellar explosions, occurring in galaxies billions of light years away, appeared dimmer than expected for their measured recession speeds. The only explanation that fit the data was that expansion is accelerating rather than slowing. Distant galaxies are flying apart faster now than in the past. Some unknown influence opposes gravity's attractive pull, driving cosmic acceleration. Physicists name this mysterious component dark energy because it exerts negative pressure, effectively anti-gravity on cosmic scales. Current measurements indicate dark energy comprises roughly 68% of the universe's total energy budget. Ordinary matter, everything made of atoms including stars, planets and living things, accounts for less than 5%. Dark matter, another mysterious component detectable only through gravitational effects, makes up about 27%. The majority constituent of reality is something we cannot see, touch, or directly detect except through its influence on cosmic expansion. The simplest explanation invokes the cosmological constant, a term Einstein added to his field equations in 1917, then later rejected. This constant represents energy inherent in empty space itself. a uniform energy density pervading the vacuum. Einstein originally introduced it to create a static universe, balancing gravitational attraction, but abandoned the idea after Hubble's discovery showed the universe expands. Decades later, observations resurrected the cosmological constant as the leading candidate for dark energy. If vacuum possesses intrinsic energy with negative pressure, it would produce exactly the observed acceleration. However, calculating what value this vacuum energy should have produces one of physics' most embarrassing failures. Quantum field theory predicts virtual particles constantly appearing and disappearing even in empty space, contributing energy to the vacuum. When physicists calculate this quantum vacuum energy, they obtain a number roughly 10 to the 120th power larger than the observed cosmological constant. This mismatch between prediction and observation is the worst discrepancy in scientific history. Either quantum calculations are fundamentally wrong, which seems unlikely given their success elsewhere, or some unknown mechanism cancels almost all vacuum energy, leaving only the tiny observed amount. Why the cancellation would be nearly but not exactly perfect, leaving just enough energy to cause acceleration, remains utterly mysterious. Alternative models propose dark energy isn't constant but changes over cosmic history, possibly a dynamic field similar to those driving inflation in the early universe. Observations haven't detected any variation, but current measurements lack precision to rule out subtle evolution. Without understanding what dark energy is, we cannot predict whether acceleration will continue indefinitely, eventually weaken, or perhaps even reverse. The nature of this dominant cosmic component and the explanation for its bizarre, small yet non-zero value represent profound gaps in our understanding of spacetime's large-scale behavior. How can our most precisely tested theory produce a prediction that misses reality by 120 orders of magnitude? And what does this catastrophic failure reveal about gaps in our understanding? Quantum field theory, the framework describing electromagnetic, weak, and strong forces with extraordinary accuracy, makes a definite prediction about empty space. Even in perfect vacuum, quantum uncertainty ensures fields constantly fluctuate. Virtual particle pairs spontaneously appear and annihilate, borrowing energy from uncertainty for brief instants before repaying the debt. These fluctuations contribute energy to the vacuum itself, creating a baseline energy density even where no real particles exist. Calculating this vacuum energy involves summing contributions from all possible wavelengths. Longer wavelengths contribute little, but as wavelength decreases, energy per mode increases. The sum diverges toward infinity unless you introduce a cutoff, some minimum wavelength beyond which the calculation stops being valid. Using the Planck length as a natural cutoff gives a vacuum energy density of roughly 10 to the 94th grams per cubic centimeter. Converting this to the cosmological constants units and comparing with observations reveals disaster. The measured dark energy density is approximately 10 to the minus 29 grams per cubic centimeter. Quantum prediction exceeds observation by a factor of 10 to the 123rd, making this the worst quantitative mismatch between theory and measurement in physics history. If vacuum energy were as large as predicted, the universe would have expanded so rapidly that galaxies, stars, and atoms could never have formed. The discrepancy isn't a minor correction or missing factor. It's a fundamental breakdown suggesting something deeply wrong with either quantum field theory's application to gravity or our understanding of vacuum's nature. Several explanations have been proposed, none satisfying. Perhaps some unknown symmetry forces positive and negative contributions to cancel nearly perfectly, leaving only the tiny observed remainder. Supersymmetry relating particles with different spins could potentially achieve this cancellation, but requires every known particle to have an undetected partner. No evidence for supersymmetry has appeared despite extensive searches. Even if supersymmetry exists, explaining why cancellation is imperfect, leaving precisely the small observed value, requires additional assumptions. Another approach suggests the cosmological constant's value is environmental rather than fundamental. In a multiverse containing regions with different vacuum energies, only those with small values permit structure formation and observers. We necessarily find ourselves in a rare region where dark energy is small because larger values preclude life. This anthropic reasoning explains the observed value's smallness, but not its origin or why the multiverse exists. It trades one mystery for another. Some theorists propose vacuum energy isn't fundamental but emergent, arising from quantum entanglement structures or holographic boundary information. If space-time itself emerges from deeper quantum processes, perhaps dark energy represents a feature of that emergence rather than a property of fields in space. These ideas remain speculative without concrete implementations. The cosmological constant problem represents more than a calculational failure. It signals disconnect between quantum field theory and general relativity at their foundations. Vacuum energy should gravitate curving space-time according to Einstein's equations. Quantum mechanics provides a definite answer for how much energy vacuum contains. General relativity specifies how that energy should affect cosmic expansion. Yet combining these predictions produces nonsense. This suggests the two theories, despite working magnificently in their respective domains, cannot simply be merged. Something fundamental about either, quantum vacuum or gravitational response to energy density, must be misunderstood. Resolving this requires more than technical corrections. It likely demands reconceptualizing what vacuum energy or space-time means at the deepest level. Until then, we're left with the uncomfortable fact that space-time's large-scale evolution depends on dark energy, whose nature and value we cannot explain. The universe accelerates for reasons we've measured, but don't comprehend, driven by the dominant component of cosmic content that remains utterly mysterious despite determining space-time's ultimate fate. What will be the final state of the universe trillions of years from now? And why does answering this question require understanding the mysterious force currently tearing space-time apart? The cosmos faces three fundamentally different possible fates depending on how dark energy behaves over cosmic timescales. If acceleration continues strengthening, as would happen if dark energy density increases while space expands, the universe approaches a big rip. In this scenario, expansion eventually overwhelms all forces holding structures together. First, galaxy clusters unbind as space stretches faster than gravity can hold them. Then individual galaxies dissolve, their stars flung apart by accelerating expansion. Solar systems disintegrate next when stretching exceeds gravitational binding between planets and suns. Eventually, expansion grows violent enough to tear apart stars themselves, then planets, then molecules, then atoms, and finally even atomic nuclei and elementary particles. Space-time literally rips matter into constituent pieces at progressively smaller scales until nothing remains bound together. The universe ends in complete isolation, every particle separated from every other by ever-increasing distances. This fate requires dark energy to strengthen over time, something current observations neither confirm nor rule out definitively. If instead dark energy remains constant at its present value, matching the cosmological constant hypothesis, acceleration continues indefinitely, but gradually weakens relative to matter's influence as the universe expands. This leads toward the big freeze, sometimes called heat death. Galaxies continue receding, and after trillions of years, all but the closest gravitationally bound neighbours disappear beyond cosmic horizons. Star formation ceases when gas supplies exhaust. Existing stars burn out one by one. Black holes evaporate through Hawking radiation over timescales of 10 to the 100 years. Eventually, only isolated particles remain in vast darkness, space expanding forever while temperatures approach absolute zero. Energy spreads uniformly, eliminating all gradients needed for work or complexity. The cosmos becomes a cold, dark, maximally dispersed state where nothing interesting can ever happen again. Entropy reaches its maximum, and the arrow of time effectively disappears because no further change occurs. A third possibility emerges if dark energy weakens or reverses sign, something permitted by the models where it represents a dynamic field rather than constant vacuum energy. If expansion slows and eventually reverses, gravity regains dominance and the universe begins contracting. This big crunch mirrors the Big Bang in reverse. Galaxies approach each other, then collide and merge. Space shrinks, compressing matter and radiation to higher densities and temperatures. Background radiation grows hotter as wavelengths compress. Eventually, stars evaporate in the increasing heat. Atoms break apart. The universe collapses toward a final singularity where all matter and space-time crush to infinite density. Whether this singularity represents genuine end or transition to another cycle depends on quantum gravity physics we don't understand. Current observations favour either constant dark energy leading to freeze or slightly increasing energy trending toward rip. Measurements show no evidence for weakening that would permit crunch. However, precision remains insufficient to distinguish between scenarios definitively. Dark energy's properties over cosmic timescales might differ from present behaviour, in ways undetectable with current technology. Without understanding what dark energy fundamentally is, predictions become extrapolations of limited data rather than derivations from physical principles. The ultimate fate is not merely unknown, but unknowable given current theory. Solving the dark energy mystery is essential for predicting spacetime's destiny, because the answer determines whether expansion continues, accelerates catastrophically, or reverses. This represents one of cosmology's most profound open questions. Spacetime's future evolution, the ultimate context for everything existing within it, depends entirely on understanding the mysterious component dominating cosmic dynamics, yet resisting every attempt at explanation. After more than a century of investigation, what have we actually learned about spacetime, and why do our greatest successes somehow make the remaining puzzles more intriguing rather than less? Consider the extraordinary journey from Einstein's initial insights to today's understanding. We've confirmed beyond any reasonable doubt that spacetime is genuinely curved by mass and energy. Precision measurements verify time dilation effects to parts in trillions. GPS satellites function only because engineers account for both velocity and gravitational time shifts. Gravitational waves predicted in 1915 were finally detected a century later, their waveforms matching theoretical calculations with stunning accuracy. LIGO hears black holes colliding across billions of light years, translating spacetime ripples into data that confirms Einstein's mathematics in the most extreme conditions. The Event Horizon Telescope assembled a planet-sized instrument to photograph a black hole's shadow, revealing geometry exactly where general relativity predicts it should appear. Frame dragging around rotating bodies has been measured. Light bending around massive objects is now routine astronomy. Binary pulsars lose orbital energy at precisely calculated rates as they emit gravitational radiation. Cosmological observations trace the universe's expansion across 13.8 billion years using spacetime curvature as the fundamental framework. Every technological application, depending on relativistic corrections from particle accelerators to satellite communications, validates the theory daily through successful operation. These achievements represent physics operating at its finest, taking abstract mathematics and demonstrating it describes reality with precision once unimaginable. We don't merely believe spacetime curves. We've measured the curvature, mapped it around various objects, detected its dynamic oscillations, and built civilization partially upon understanding its properties. Yet this very success throws fundamental mysteries into sharper relief. We know that spacetime curves, but not what curves. We can calculate how geometry responds to mass without understanding what geometry ultimately is. Does spacetime possess substance, or is it pure mathematical relationship? Is it fundamental fabric or emergent property arising from deeper quantum structures? These questions remain unanswered, despite experimental triumphs. The conflict with quantum mechanics persists unresolved. General relativity and quantum field theory both work magnificently within their domains, yet cannot be combined consistently where both should apply. Black hole interiors and the universe's first moments remain mysterious because we lack the physics to describe them. Whether spacetime is smooth or discrete at Planck scales, whether it emerges from entanglement or exists fundamentally, whether holography captures something essential or misleads, all these questions stay open. Dark energy dominates cosmic evolution while remaining completely unexplained. The cosmological constant problem represents theoretical failure on an unprecedented scale. Time's arrow and the distinction between past and future have no clear foundation in spacetime's mathematical structure. The feeling of temporal flow contradicts block universe implications without any resolution. In some sense, our knowledge has deepened the mystery. Before Einstein, we didn't know enough to ask the right questions. Newtonian absolute space and time seemed perfectly adequate. Only by discovering relativity did we learn that reality is stranger than imagined, that space and time interweave, that geometry participates dynamically in physics. Each answer revealed new puzzles. Confirming gravitational waves required understanding quantum mechanics' incompatibility with general relativity. Measuring dark energy exposed our inability to calculate vacuum energy correctly. Imaging black holes highlighted how little we comprehend singularities. Progress hasn't eliminated mystery. It's refined and focused it, showing us precisely where understanding breaks down. We've mapped the boundaries of current knowledge with remarkable clarity. The mysteries aren't vague hand-waving about things we might never understand. They are specific technical problems with defined characteristics. We know what we don't know, and that knowledge itself represents progress. The deepening mystery isn't failure, but invitation, showing exactly where future physics must venture to expand understanding beyond current limits. What if the ongoing mysteries surrounding space-time represent not gaps waiting to be filled, but permanent features of how science engages with reality? And why might incomplete understanding be more valuable than having all answers? The popular image of scientific progress imagines a steady march toward complete knowledge, each generation filling gaps left by predecessors, until it's eventually a final theory explains everything. This picture misleads because it assumes nature's depth is finite, that eventually we'll reach bottom and understand reality completely. History suggests otherwise. Every major breakthrough in physics, rather than closing investigation, opened new territories for exploration. Newton's mechanics prompted questions about gravity's mechanism and absolute space's nature. Thermodynamics led to statistical mechanics and quantum theory. Relativity revealed spacetime's curvature while creating puzzles about quantum gravity. Each solution spawned further mysteries, a pattern suggesting the universe's explanatory depth exceeds any finite theory's reach. Spacetime exemplifies this beautifully. We've achieved extraordinary understanding, confirming curved geometry, detecting gravitational waves, testing predictions to remarkable precision. Yet fundamental questions about spacetime's ultimate nature remain entirely open. Is geometry emergent or fundamental? Does spacetime have substance or represent pure mathematical structure? What replaces it at Planck scales? These aren't temporary gaps awaiting clever solutions, they're indicators that our current framework, however successful, isn't the final story. This incompleteness isn't scientific failure but honest acknowledgement of where understanding currently stands. Pretending to know what we don't would be failure. Recognizing limits while continuing investigation represents science functioning properly. The mysteries invite continued exploration rather than frustrating incomplete knowledge. They show where new physics likely hides, where future breakthroughs might emerge, where young researchers can make genuine discoveries rather than merely refining known theories. Not knowing spacetime's fundamental nature means the question remains alive, actively investigated, potentially revolutionary. Moreover, the universe operates under no obligation to make sense according to human intuitions or preferences. Quantum mechanics violates common sense regularly. Spacetime's geometry contradicts everyday experience of separate space and time. Dark energy's existence seems almost designed to baffle us. Reality doesn't care whether its structure seems reasonable or elegant or understandable to creatures who evolved to hunt prey and gather food on an African savanna. Our brains developed to navigate medium-sized objects at moderate speeds, not to intuit quantum mechanics or relativistic spacetime. The fact that we've understood as much as we have, extending comprehension from everyday scales to subatomic particles and cosmic horizons, represents extraordinary achievement given our cognitive limitations. Expecting complete understanding might be hubris, assuming the universe owes us transparency. Perhaps some aspects of reality lie permanently beyond human comprehension, not because we lack cleverness, but because our cognitive architecture cannot represent certain structures. Alternatively, maybe every mystery eventually yields to investigation, but the process never completes because each answer reveals richer questions. Either way, incomplete understanding becomes the natural state rather than a temporary condition awaiting resolution. This perspective transforms how we regard spacetime's mysteries. Rather than frustrations blocking progress toward final truth, they become invitations to wonder, opportunities for discovery, indicators of reality's inexhaustible depth. The beauty lies precisely in not having finished, in possessing powerful partial understanding alongside recognition of how much remains unknown. Spacetime curves, warps, ripples, and stretches according to equations we've tested thoroughly. It also might be emergent, holographic, discrete, or something entirely unanticipated. Both statements can be simultaneously true because science describes reality through provisional models subject to refinement rather than discovering absolute eternal truths. The incomplete understanding keeps inquiry alive, prevents complacency, and maintains science's dynamic character where questioning never stops and mystery always beckons from just beyond current knowledge's edge. As you settle into whatever position feels most comfortable right now, have you noticed that you're travelling through curved space-time at the speed of light, following geodesics shaped by Earth's mass, the Sun's gravity, and the collective pull of our galaxy? Every breath you take traces a path through four-dimensional geometry. Each heartbeat marks progress along your personal timeline through the fabric Einstein revealed. The pillow supporting your head experiences time slightly faster than the mattress beneath your feet because gravity weakens with altitude, making temporal flow depend on position in ways too subtle for consciousness to detect, yet precise enough for atomic clocks to measure. Right now, this very moment, space-time curves around you, through you, and because of you. Your body's mass contributes minutely to local geometry, bending the fabric in ways that would require extraordinary instruments to detect, but are nonetheless real. The mystery we've wandered through together isn't distant or abstract. It surrounds you completely. The strangeness of quantum foam potentially churning beneath Planck-scale smoothness, the puzzle of whether geometry emerges from entanglement, the question of what dark energy is and why it dominates cosmic evolution. All these mysteries form the backdrop for this quiet moment. You exist within the puzzle rather than observing it from outside. Not understanding space-time's ultimate nature tonight is perfectly fine. Actually, it's more than fine. It's an invitation to rest within mystery rather than demanding resolution. Some questions aren't meant to be solved during a brief lifetime, but to be lived with, contemplated gently, appreciated for their depth rather than attacked for their resistance. The universe has spent 13.8 billion years unfolding its geometry, creating conditions for matter to clump, stars to ignite, planets to form, and eventually beings capable of wondering about the fabric holding it all together. That wondering is itself remarkable, a consequence of space-time's curvature creating gravitational wells where chemistry becomes complex enough to produce thought. You are the universe examining itself, curved space-time contemplating its own nature. Let the strangeness be a companion rather than a problem requiring immediate solution. The fact that simultaneity is relative, that time flows differently at different heights, that space itself expands carrying galaxies apart, that black holes exist with event horizons hiding singularities we cannot describe, none of this needs to make perfect intuitive sense tonight. It can simply be what it is, strange and beautiful, and deeply mysterious even after a century of investigation. As sleep approaches, you might find comfort in knowing that the greatest minds across generations have grappled with these same puzzles without reaching final answers. Einstein died without understanding quantum mechanics' implications for his geometric theory. Hawking spent decades wrestling with black hole information paradoxes. Thousands of physicists currently work on quantum gravity, emergent space-time, and dark energy without consensus. You're in good company allowing these questions to remain open, unanswered, gently present in the background of awareness. Every moment you've existed, you've been moving through space-time without needing to understand it. Ignorance about geometry's fundamental nature hasn't prevented you from navigating reality successfully. You've walked through curved space, aged through flowing time, and experienced the arrow carrying you from past toward future without consciously grasping the framework making it all possible. Perhaps that's the final thought to carry into sleep. Space-time works perfectly well without demanding comprehension. It curves, stretches, ripples, and evolves whether or not anyone understands why. The mystery is patient, content to remain mysterious while supporting the reality where questioning happens. If you found this gentle exploration helpful for settling into rest, it would mean a great deal if you'd consider liking the video or subscribing. It helps others discover this quiet space where science and wonder meet without urgency or pressure, but only if it feels right. For now, let space-time carry you gently into sleep, its mysteries intact, its strangeness softly surrounding you.